Hello friends, I am Ms. Divyarekha Maharana, Assistant Professor in the Department of ECE, St. Peter's Engineering College, Hyderabad. Today I am going to discuss the topic 8086 microprocessor. Here I am going to cover what is microprocessor, the generation of microprocessor, 8086 microprocessor architecture, its addressing modes, the instruction set used, the assembler directives and operator, how to programming with 8086, interfacing memory and I/O port, as well as comparison of 8086 and 8088. Now come to what is a microprocessor. A microprocessor is a program-controlled semiconductor device or an integrated circuit which fetches the instructions available in memory, decodes and executes it and provides the result. It is also used as a central processing unit in the computers. Let's come to the generation of microprocessors. Here we can see there are 5 generations of microprocessors. The first generation came in between 1971 to 1973, which uses CMOS technology and it is non-compatible with TTL. The first generation processors are 4-bit processors as well as 8-bit and 16-bit processors. The 4-bit processors came in 16 pins, whereas 8 and 16-bit processors came in 40 pins. In first generation processor, the limitation is the number of pins. So, due to the number of pins are less, the signals are multiplexed. In first generation microprocessor, you can see the 4-bit processors are 4004, Intel 4004, and 8-bit processor is Intel's 8008. In second generation, the second generation came during the year 1973, which uses NMOS technology, which provides faster speed, higher density, and it is also compatible with TTL. In second generation processors also, there are 4-bit, 8-bit as well as 16-bit processors having 40 pins. It has the ability to address large memory spaces and I/O ports, and it has greater number of levels of subroutine nesting and better interrupt handling capabilities. Example is your Intel's 8085 processor, which is a 8-bit processor. Let's come to the third generation, which came during 1978, which uses HMOS technology. So HMOS technology provides faster speed, higher packing density. The third generation processors are 16-bit processors are available with 40 pin, 48 pin as well as 64 pins. It is easier to program. It has dynamically relatable programs. It has some advantages like processor has multiply and divide arithmetic hardware, or you can say multiply or divide instructions are available, which is not available during the second generation. It has more powerful interrupt handling capabilities and flexible I/O port addressing. Let's come to the fourth generation. It came during 1980s, which uses low power version of HMOS technology, which is called as the HCMOS. 32-bit processors came. It has having a physical memory space of 16 MB and virtual memory space of 1 TB. It uses floating point hardware and it supports increased number of addressing modes. Example, Intel's 80386. Next, fifth generation is the Pentium processors. Pentium 1, 2, 3, 4 all came under fifth generation of processors. Nowadays, Itanium 3, that is i3, i5 and i7 processors are coming, which you can put in sixth generation of processors. Next, we will discuss about the functional blocks of microprocessor. Here in this diagram, we can see there are 6 functional blocks, as well as here we are having the buses. Here you can see the system bus is having 3 buses: data bus, address bus and control bus. Data bus is bidirectional, address bus is unidirectional and control bus is bidirectional. Here you can see these 6 units are connected with the buses. Here the major unit is the timing and control unit, which is connected to register array as well as instruction decoding unit, to the flag register as well as to the ALU and to the program counter or the instruction pointer. Hence this timing and control unit is connecting to all the remaining 5 blocks. Now we will discuss the function of each block. Now first come to see the data bus. From the data bus, the data will be entered into the register or the memory. From this register or memory, the ALU is going to collect the data. Whether the data will be collected from register or the data will be written into the register, that is going to be decided by the timing and control unit. The timing and control unit is going to provide the control signals, whether it's a memory read write or IO read write. If read means the ALU is going to read the content from register or memory, write means the ALU is going to write the content of the ALU or the result output into the register or memory. Next is the instruction decoding unit. Instruction decoding unit, it is going to decode the instructions and provides the timing and control signals. Whatever the result will come after the operation in the ALU, that is arithmetic and logic unit, it is going to perform all the arithmetic and logical operations. Whatever the operations is going to be performed by the ALU, the result will come, and the condition of the result is going to be shown by the flag register. You can say the condition or status of the result is going to be shown by the flag register. In 8086 processor, it's a 16-bit flag register having 9 flags activated and rest 11 pins are deactivated. Next come to the program counter and instruction pointer. It is having a major role. What is the function is going to be provided is it is used to generate the address of the instruction to be fetched from the memory and sent the address bus to the memory. Suppose you have a program, you have written a set of instructions back to back. So, what is the process of execution of that instructions and how the instructions are going to be executed by the processor? That is going to be shown by the program counter or instruction pointer. So, you can say the program counter or instruction pointer gives the sequence of execution. Sequence of execution means where the next instruction is present, that memory location is going to be given by the program counter or instruction pointer. So, we will discuss about 8086 processor. So, 8086 processor is the first 16-bit processor released by Intel in the year 1978. It uses HMOS technology. It is having approximately 29,000 transistors. It comes under 40-pin dual inline package with 5-volt supply. It doesn't have an internal clock. An external asymmetric clock source is there, which provides 33% duty cycle. It has 20-bit address bus and 16-bit data bus. So 20-bit address bus is going to access memory of 1 MB, 1 megabyte memory space, and this addressable memory space is divided into 2 banks. That is of each of 512 kilobyte. One is even bank, one is the odd bank. Even bank is known as the lower bank, odd bank is known as the higher bank. So how to choose between even bank and odd bank? For that, the address line A0 as well as the control signal DHG bar is an active low control signal at bus high enable. It is used to access the odd bank. So, having 16-bit data lines, it can generate up to 64 kilobytes of address. The 8086 processor can operate in 2 different modes. One is the minimum mode, another one is the maximum mode. And in which mode it is going to operate, that is going to be decided by a signal, that is mn/mx bar. When mn is this pin is equal to 1, then it will operate as in minimum mode, that is single processor mode. When this pin is equal to 0, means it is going to operate in maximum mode, that is the multiprocessor mode, or number of processors can be joined to the 8086 microprocessor and it can be operate on that mode. Next we will discuss what is the pin diagram of 8086 processor, or what are the pins and signals are available in 8086 processor. Here you can see 8086, as I said, it's a dual inline package with 40 pins are there. Out of 40 pins, here we can see the first pin is the ground, 40 pin is the VCC, and 20 pin is also the ground. For better use, there are 2 pins present which is acting as ground. Except that you have some common signals. Common signals is nothing but here you can see the shaded signals, that is from AD0 to AD14, AD15, AD16/S3, AD7/S4, AD18/S5, AD19/S6. AD0 to AD15, that are bidirectional pins, that is nothing but multiplex address and data bus. So AD0 to AD15, the AD lines are used to transmit memory address. A is used for transmitting address, D is used for transmitting data. A16 to A19 with status signals S3, S4, S5 and S6 has been used. These address lines are multiplexed with the status signals. Next come to the BHE bar class S7. This BHE bus high enable signal is also multiplexed with the S7 status signal. It is also an output signal. It is used to enable data onto the most significant hub of the data bus, that is D8 to D15. 8-bit device connected to the upper hub of the data bus use the BHE signal and it is multiplexed with status signal S7. As I told you before, the MN/MX bar is used to decide the processor is going to operate in which mode, whether in minimum mode or single processor mode or in maximum mode, that is multiprocessor mode. Read is the active low signal. This signal is used for read operation. It is an output signal and it is active when low. Means when 0, the pin is going to be active and the processor is going to read from the memory or the I/O device. Next is the test input. That is test bar. It is also an active low signal. The test input is tested by the wait instruction. 8086 will enter into a wait state after execution of the wait instruction and will resume execution only when the test is made low by an active hardware. This is used to synchronize an external activity to the processor internal operation. Let's come to the ready signal. This is an acknowledgement from the slow device or memory that they have completed the data transfer. Let's say when the processor works in multiprocessor mode, there are so many processors are going to connect to the 8086 processor. So when the processors are slow, that they cannot carry the data to the 8086 processor, then at that time the 8086 microprocessor is not ready. So when the connecting processors are more enough speed or they are synchronously connected to the 8086, means the ready signal is going to be activated. And it says that yes, the other peripherals are activated, ready to process. So this is an input signal and this is an active high signal. The signal is made available by the devices is synchronized by the 8284A clock generation to provide ready input to the 8086. Then come to the reset input. It causes system reset when it is high. Then clock, as I told that an external clock is going to be connected here which provides 33% duty cycle. Then interrupt request, INTR, this is a triggered input. This is sampled during the last clock cycle of each instruction to determine the availability of the request. If any interrupt request is pending, the processor enters the interrupt acknowledgement cycle. This signal is active high and internally synchronized. Let's come to the minimum and maximum mode pins. Here it is highlighted what are the minimum mode pins and maximum mode pins. As I told you earlier, how the minimum mode and maximum mode is going to be operate with the help of this pin. Now I will discuss what are the pins are available in minimum mode. First is DT, data transmit and receive. This is the output signal from the processor to control the direction of data flow through the data transceivers. Similarly, next one is your data enable. It is an output signal from the processor used as output enable from the transceivers. ALE, that is address latch enable, which is used to demultiplex the multiplexed address and data lines. M/IO bar, if it is active high means memory related operations are going to perform. If it is active low means IO related operations are going to perform. Write bar, this is a write control signal which is active low. Whenever it is activated, whenever the processor wants to write the data into the memory or IO port. Next, the last is your interrupt acknowledge, INTA bar. Again, it is an active low signal. When it is going to be activated, when the interrupt request is accepted by the processor, the output is low in this line by saying that the interrupt request has been accepted. Next is your hold. Hold and HLDA, both hold and hold acknowledge. They are used for DMA controllers. When a DMA controller wants to access the system bus of the processor, at that time it will send the hold signal, and if the processor is ready to give access to the system bus, then it will send the acknowledge signal, that is HLDA. Now come to the status signals S0 bar, S1 bar, S2 bar. These are nothing but the maximum mode signals. So maximum mode signals, these three signals are going to show the status. These three signals is having 8 combinations. In 8 combinations, the different machine cycles are going to be generated. That is when 000 interrupt acknowledge, 001 read IO port, 010 write IO port, 011 halt, 100 code access, 101 read memory, 110 write memory, 111 that is inactive or passive. Next is the queue status, QS0 and QS1. The 8086 microprocessor is having two units, that is execution unit and bus interface unit. These two units are connected through an instruction queue. That queue status is going to be shown by these two signals, QS1 and QS0. So based on this, the operation is going to be performed. If 00, then there is no operation. 01 means first byte of an opcode from queue. 10 empty the queue. 11 means it will collect the subsequent byte from the queue. Next is your request and grant. Request and bus grant, like old and HLDA is used in minimum mode for DMA operation. Similarly, here also for DMA operation, for request and grant is going to be used, but here at a time two processors can accept the request. It can take the request to accept the master bus system bus, and it can be used. The next is your lock bar. The 8086 output low on the lock pin while executing an instruction prefix by lock to prevent other bus masters from gaining control of the system bus. If lock bar pin is active, means if it is low, means no one is going to access the system bus. In the next video, I will discuss about the architecture of the 8086 processor.